of this main distribution panel. Okay, so it depends on location. So therefore, if it's in the second floor, so probably you'll have longer length from Kaisha conductor gamut will be longer than this DP1. Okay, so therefore the voltage drop here will be significant than the voltage drop here in this feeder. Okay, so let's say that we have here the same conductor size. So that is, let's say we are using 38 mm squared, and here also 38 mm squared. So by just knowing the rating of these feeders, let's say we already have identified or determined based on the calculation that this feeder will take 68 ampere. Okay, so given the demand, the rated demand for this feeder. Okay, so since that is the maximum, although that's not always the case, but we have to base our calculation on this one. Okay, so since we have this current, so we also know the conductor size, and based on your design, since you have the three-dimensional units of your floor plan. So therefore, you can now calculate so the distance of this conductor or the length of this conductor. Okay, so that will be this will serve as your kind of parameters for your voltage drop calculation in the feeder. While for your branch circuit calculations, you have to base it on these conductors. So in our example kind of design, so we already have determined how to calculate this. Depends on the load that is really being served by this feeder. Okay, so actually the calculation here really differs from state to state. For example, in US, they have different calculations. So some state requires that you use the current here instead of using the demand. No, so some uses the rating full rated current of this branch circuit. So let's say this is 20 ampere branch circuit. So ang multiplier sa niya is automatically 20 ampere. Even if the load, for example, here is just a lighting load. So let's say the actual load is just, or the total connected load is just 4 ampere. Okay, so if we calculate it based on 4 ampere, so surely the voltage drop will be lesser than this rated current calculation. So again, it depends on the state requirement also. Then for some, they are also to be safe. So even if we're not using the full load or rate capacity of this conductor, so some state uses this multiply them if this is the demand 68 amperes, so they multiply it first by 1.25. Okay, so to satisfy also the requirements, some part of the code where we need to use only 80% of our conductor size. Okay, then, yeah, so but in our case, so we just have to look at the demand of each of these branch circuit, then that's what we're going to use in our calculation. Okay, so again, this is the feeder calculation, and this is branch circuit calculation. So therefore, the more branch circuit you have, the more calculation you need to provide. But that is that's what we're going to do because we're still practicing, but in actual na gid nga mga design, so dili na siya ipakita tanan dire because it is oftentimes, as long as you follow again the code where you the sizes here are based on the requirements of the code. So it's not it's very unlikely for you to obtain here a voltage drop that is greater than the required voltage drop percentage by the code. Okay, so in our case, we're going to show this by some examples. Okay, so now, so since we only have this if we only have one floor nga building, so usually automatically this na siya ang imuhang main is already within your main panel board as well. Okay, so therefore, in our calculation, so we'll just base our feeder calculation on this one, on this conductor. So from the service point, to your panel board. So this conductor is based man siya sa imong total demand. So in our case, in our previous example, no. So yeah, so this conductor, so service entrance is here, but this will also serve as the feeder for this panel board alone. Okay, and also we are going to use this current. Okay, so this is the demand for this for that kind of conductor. So therefore, we use this as our in the calculation of voltage drop. And also for the for each of these branch circuits. So again, we have to base it on this uh, current instead of the rating of each branch circuit. So how do we calculate that? So very simple lang ang calculation. So we just follow the Ohm's law. But in this case, since we are using AC, so we based our calculation that is equal to I times Z. So we already have here our I, so based on our demand, and we just gonna look up for Z in the table. Okay, so that's in table 9, I mean chapter 9, table, yeah, so also table 9. Okay, so for AC. Okay, so let's try this one. Let's try to calculate this one. So for some mga practitioners, so they are going to use this table, so in which na siya yung format, no? So also the table 9 is already here where you can just look up for values. So automatically, once you have here your current, for example, mo na siyang input, so it will automatically calculate for the values. So what we're going to do here is do these calculations. Okay. So let's work on with this previous example. So let's start with the service entrance. Okay, so again, we have here this current, so 86 amperes. So, and according to our according to table 310 15b16, so the conductor that we need to use for this calculation is, I mean, for this current is 22 mm squared. Then, by the way, so I'll just have to take note here that if you are going to have a design for AC, single phase, so you have to multiply your values by 2. Okay, so because the distance from your service point to your service equipment is wala na siya ang one line lang siya. So for the return, so we need to multiply it by 2. But for three phase, okay, so we need to multiply it by 1.732. Okay, so whatever is the load, so multiply by 1.732. So just the square root of 3. So let's because this is single phase now, so we focus on this one. And so start with this one. So first, you have to determine the demand. Okay, so in our case, we already have determined the demand for this dwelling unit, so that is 86 amperes. Okay, so demand. Can you still hear me?
Yes, sir.
Murag kayo akong audio, no? So lahi kayo sa ako ang gi-present problem. Okay, so I'll just switch between tabs lower. Um, yeah, so here, so we already have identified that we are going to use squared, 22 squared, th plus th hn. Then all we have to do now is look for the value of the resistance and reactance for this conductor. Okay, so that is located in table chapter 9, table 9. Okay, so for AC. So I'm going to use again now the this National Electrical Code, because in my copy of the Philippine Electrical Code, so until chapter 8 lang siya. So wala ko copy sa Philippine Electrical Code. Okay, so I go now to chapter 9. So have it here bookmarked. Okay, so chapter 9. Oh, so I was wrong now. So chapter 9, table 8. Okay, so table 8, so this is table 9. So this is table 8. And again, we have to look up for the resistance and reactance of this conductor. Okay, so that is 22 mm squared. So 22 mm squared, so that is number 4. So actually, nasa equivalent. So 21.15, so that is 4 mm squared. And it's approximately equal to 22. So therefore, we use this number for AWG. And actually, that's the trade size for number 4 AWG, no? So 22 mm squared. So we look up, so table 8. So actually, wrong siya, no? Because this is their current. So sakto lang gisulti ko din, no? Dapat na sa chapter 9. So table 8 is for direct current. So for DC lang na siya calculation. And table 9 is for AC. Okay, although take note na this can also be used for three-phase as long as you are considering only the single conductors. Okay, so table 9. So let me just correct this one. So table 9, and okay, then number 4. So this is number 4. Okay, so if you look at here, so in this column, so this is the reactance for all wires. Okay, so kaya siya. Then you also have to consider na unsa ang imuhang what do you call that? Ang imong gamiton nga conduit. Okay, so if you are going to use steel conduit, so you base your calculation on these values. Okay, so ano siya ang babaw? 197 is for where is it? So this one, ohms to neutral per kilometer. Then ito siyang ubos nga value is for ohms to neutral per 1,000 feet. Okay, so therefore, let's say wala pa tayo specification. So we also need to determine. Okay, so anyway, later na, since this is for ako lang siya specify that this is per, let's say we are going to use per meter, no? Per or 1 kilometer na lang. Okay, term dire. 1 km So again, the first value is for per kilometer, then the second value is per so that is my XL. Okay, so 0.157 ohm, ohm per 1 kilometer. Okay, so number four, okay, that's correct. Then for your resistance, so you have to look at this value. Okay, so alternating current resistance for uncoated copper wires. Okay, so since ang ako, ano, conduit is PVC, so I have to look at this column here, PVC. Then number four, so this is 1.02 ohm, 1.02 ohm per 1 kilometer. Okay, so with these values now, so you can now start calculating your voltage drop. So as long as you have so the actual, let's calculate first for the actual resistance. So based on uh, length, is the correct spelling? Length, that is, let so in this case now, so wala pa tayo land, so we have to assume lang. Okay, so in your case, since you know the layout of your of your wirings, and yeah, so the dimensions that, so therefore you can estimate the length of your conductors. Okay, so in this case, let's just say that we are going to for the feeder because this is for residential lang building. So therefore, usually where you locate your feeder, I mean main panel board is closer to your service point. Okay, so probably just have around 5 meters. Okay, so we have here 5 meters. Okay, so or again, it depends now. So to be safe, let's just say this is 10 meters. Okay, so 10-meter ang distance of your service point to your main panel board. Okay, so therefore, when you calculate now for the total impedance, Z, we based it on these values. So I'm just going to multiply this by this number. Okay, so that is the square root of 1.02, but this is 1 kilometer, so therefore, pila man ni siya, mahimo ni siyang 0.01. 0.01, okay, so 1,000, yeah, so that's correct. So 0.01, this will be your resistance for this 10-meter conductor. Okay, then plus, so yeah, so times plus this one, 0.157, again, 0.01 squared. Okay, so let me just calculate here. So I have um, 1.02, 0.01 squared plus 0.157, 0.01 squared So I have here 0.01, 0.01032. Okay, so this is correct now. So this will be my Z for just one line. Okay, then when we calculate now for our voltage drop, so V is equal to V feeder is equal to, so the current, so 2 times, because we have here, again, this is just for one line, so we have to calculate for the single phase impedance, so that is 2 times this value, 2ZL1, or one line, times the current. So this is the demand, so that is 86. Okay, so this will be now our voltage drop. So 2 times 0.01032 times 86. Okay, so the voltage drop is just 1.78 volt. Okay, so gabay lang kayo siya nga voltage drop. Then in terms of percentage, so percent VF is equal to, so since our nominal voltage is common, 230, so we based on uh, divided by 230. Okay, so that is 1.78 divided by 230 times 100%. So 1.78 divided by 230 times 100. So I have here 0.77%. So very much within the maximum limit of the National Electrical Code, so that is 3%. So therefore, this is good enough. So we can actually use this 22 m squared. By the way, no, THHN. Oh, so ako, although this is the standard calculation, but we have to look at that I'm actually using here THHN. So therefore, because if you look at this table, so this table is rated at 75 degrees. Okay, so but THHN is rated at 90 degrees Celsius. So therefore, we have to apply some adjustment, so that we can use these values here in table 9. Okay, so uh, so where is it? So here. So we can we still have to use only the resistance will change because more siya affected by temperature. Okay, so we have this alpha. Okay, so 0.00323. So let's try to use this one here. So we have to adjust this. So if we use the formula, so 1.02, so becomes, okay, so I'm going to use this. So 90 minus 75 times this factor, this is for the copper, so 0.00323, okay, then plus 1, okay, times R1. So our R1 is this value, so the value from 75 degrees times 1.02. So I have here, so at 90 degrees, so the resistance can increase to 1.069 or 1.07 per 1 kilometer or per kilometer na lang. Okay, so again, this is 75 degrees Celsius, then this is 90 degrees Celsius. So this value will be muna siya itong gamitin for our calculation. So that this is now 107. Okay, although di siya nga significant changes, no? But yeah, so we just have to take note of this because probably in your calculation, so may exceed siya sa iyang standard nga requirement. So 0.01 07 squared plus 0.00 157 squared. Good answer. So I have here 108, 1081. Or let me just stop there, 108. Okay, so this value will be used here. So this is 108 now. So 2 times 0.0108 times 86 amperes. So I have here 1.8576, 1.86 volt. 1.86 divided by 230. So this is 0.8. 0.81%. Okay, so this is my voltage drop only for the feeder. So from here, so let's say that our again, nominal voltage is 230 volt. Then pag-abot niya dire sa atong panel board, so the voltage is now so this value. So ilan to siya? 230 minus 1.86. Okay, so it became 228.14. Okay, so that is the voltage here. Then, yeah, so for the branch circuits, so we just have to, so for our example, let's select some of these branch circuits. So let's consider this water pump because naman siya usually ang pinakalayo, no? Because naman siya sa gawas. Actually, wala pa naka-determine sa current conductor din, no? But if we base it on the table, so naroon siya equivalent na value dito. Okay, so fixed bias water pump. So 8 amperes then. So let's copy it here now. So the demand is 8 amperes. Then if we look it up from the table, so we need to have, because this is 20 ampere in a branch circuit. So where is it? So 20 ampere. So therefore we are going to use number 12, THN. Okay, so 12. So by the way, now since this is water pump, so probably some part of the circuit will be outside. So, dili pwede ang THN gamiton. So, you have to use THWN. So, it has the function of THW and THHN. Okay? But for our calculation, so let's just, because anyway, THWN is also 90 degrees. So, I'm going to use here 12 AWG. So, let's just say THHN or THWN. Okay, so yeah, so we pattern our calculation here, no, para pare-pareha lang. Then again, we go to chapter 9 and obtain the value of its resistance per kilometer and reactance per kilometer. Okay, so the resistance of number 12, this is chapter 8, I mean table 8, so this is table 9. So number 12, so this one. So again, let's say that we are using PVC, no? So our reactance is 0.177. Okay, so this value. So 0.177, so that is ohm per kilometer. Okay, so while the resistance, so number 12, so this is the resistance for PVC. So we use this 6.6. Okay, so 6.6 ohm per kilometer. Okay, so again, we have to adjust this to 90 degrees. So base our calculation again on this one. So 90 minus 75. So that's the temperature difference times the factor 0.03, 00323 plus times, oh no, so plus 1 times this resistance, 6.6. Okay, so I have here 6.9 be the adjusted resistance at 90 degrees or THHN or THWN, 6.92 ohm per kilometer. Okay, so again, after this, we need to calculate for our impedance. Okay, so that is, so we have to base it on the length. So let's say that since again, if we look at it outside, let's just say that was 30 meters, and the impedance for one line is equal to, so so we multiply this by how much, how long, 30, so I think 30 is enough. 1 2, yeah, probably 30 so we multiply this by 0.03, so 6.6 times 0.03 squared plus 0.177 times 0.03. Again, this is the length. Okay, so this is squared. So that is 0.06612. Oh, sorry. Three squared plus 1 0.177 times 0.03 squared square root. Okay, so I have here 0.198, or so I'll just use this 198 ohm. Okay, so we now can calculate for the voltage drop. Equals 2, so for the return, 2 times Z1 line times the demand. Okay, so 2 times 1981 times the current at this load, so that is 8 amperes. So muna siya ang demand. Okay, so 2 times 0.1981 times 8. So we have here 3.17 volt. Okay, so percent VD is equal to 3.17. Okay, so 3.17 over. So the voltage at this point, no, is not anymore 230. So kanya siya ang voltage. 228.14. So we base now our voltage to this value, or voltage drop, percent voltage drop to that value. So 228.14 times 100%. Okay, so that is 3.17 over 228.14 times 100. So I have here 1.39%. So even if the conductor is a little bit longer now, and the conductor size is just 12 AWG, but still our voltage drop satisfies the requirement of NEC. So therefore, we can use this 12 AWG, THN or THWN. Okay, so bonus niya then, but for in your actual design guide, so you're not going to present all of these calculations here. Okay, so what we're going to present is similar with schedule load. So just a table, so containing all the information. So for example, sa kumuhang demand, so what's the demand, and also at that point, so what will be the voltage. So you see here, so same in our starting point. So we started at 230, then because this became 227 because the voltage drop here is around 3 volt. Okay, so that's for feeder voltage drop. Okay, so that's why ang starting point here is already 227. Okay, then also for some, no, ang ilang calculation is like this. So they total already the voltage drop of the branch and the feeder. Okay, so ang purpose ana is since namatay ko sa requirements of code is 5% mo ng maximum, so that we can see if nabay mo exceed sa ato ang voltage drop calculation by 5%. But even if di-add na ang voltage drop dire sa imuhang feeder and ang imuhang branch circuit, so still the total voltage drop is less than 3% instead. Okay, so more lang siya ito ipakita na. So we have to show that the voltage drop, even if we are considering the maximum loading, it's not so significant that our voltage drop or our voltage is not anymore capable of supplying the load at a better quality. Okay, so you see here 227, 226, 226. These voltages are still kind of uh, within the allowable voltage variation of the National Electrical Code or the Philippine Electrical Code. Okay, so because we have to follow, so if I remember correctly, so we can have up to 10%. Okay, so 10% of variation, voltage variation. So that is, alam mo na siya, 10%. So 220 times 10. So that's around 22 volts. Diba? So if you have 230, 230, so 10%, so that's 23. So 23 volts fluctuation from 230, so meaning you can have a voltage from around 200, around 210 to 250. Okay, so because so if this is our nominal voltage, so this is 230, again, we can have variation of 10% plus minus. Okay, so meaning we can have here around 250 volts and here around 210 volts. So with these voltages now, so we deem that this voltage is still capable of producing or supplying the specific loads. But take note that these are extreme values. So therefore, we should not operate at all times ang ato ang load at these voltages. Okay, so 250, so very dangerous na siya for the load, especially if you have your light bulbs. So if you have an input voltage 250, so it will affect the lifespan of your light bulb. Okay, so mas kusog siya musiga, but again, kamay ang lifespan. Then for 210 sad, so mas hinay siya musiga, but cause the problem is you are not getting the right illumination, for example, in your case. So if this is a motor, so what will happen to the motor? So it will take too much current. Okay, so meaning you need to increase the sad ang imuhang conductor size. But anyway, so since we already have applied some adjustment factor for the conductor, so we deem that even if the voltage dropped to 210, so within 10%, so those circuit requirements that we were able to identify from here in this design should still be enough to cater that much voltage drop. Okay, so mo na siya atong buhaton for voltage drop calculation. So you just have to show all these values now, so our specifications. So in some of these are already determined from your dwelling unit calculations, and just have to supply these kani siya mga ang bago lang diri nga values are kani siyang mga so length, for example, so you have to determine this based on the location of the for branch circuit, by the way, no. So for motor, okay na siya, so because we can easily identify the location of the motor. But for branch circuit without fixed loads, no, so you have to look at the farthest nga load. So for example, if you are going to calculate for your lighting load nga or lighting branch circuit nga voltage drop. So if this is your, for example, branch circuit for this lighting branch circuit, so we have here this load. So these are fixtures location. So we consider our calculation on the farthest load. Okay, so if this is the farthest load, so you determine what is this distance here. Okay, so muna siya ang gilayon. Then even if the farthest load will not gonna take the the total load, so let's say that the rating for this is 15 ampere branch circuit, but the total load is, or total demand is just 6 amperes. Okay, then this one, this specific load is only 1 ampere. When you calculate for the voltage drop, so we have to use yung maximum rating for that. I mean, maximum demand for that branch circuit. Okay, so we don't use this actual rating of the single load in the farthest branch circuit. Okay, so mo siya ang ato nga dapat batayan. So again, this calculation, so maybe this money. So because the requirement of the code is less than 3%, so from feeder, so take note lang sa diri sa yang from to. So in this case, so since big load man siya, so it has a its own transformer. So from transformer ang iyang calculation. But in our case, since we are just designing a residential buildings, we can just consider from the service point to the distribution panel. Okay, then here sa ato ang case from distribution panel or from branch circuit protection device to the farthest load. So muna siya ang calculation for the branch circuit. So supposedly kini siya calculation dire is uh, strictly should be just this value divided by this value, the voltage at the point where we obtain this branch circuit. So, but in this case, so to be safe, again, so kani siya nga table, kani siya nga format, basta ang maghimo gani mga mga season na nga mga practitioner, so they always play safe. So in which in their calculation, so they have to be they have to do a analysis in which their calculations are always safe. So even if there are some probably wala nila makonsider diri, but because uh, they are using this so instead of just considering the branch circuit alone, so they also consider the effect of voltage drop in the in this in the panel or feeder nga circuit. So in our case, so we can just use we can just use the per branch circuit calculation. So just like this. So our reference now is 22814. So we don't because if we are going to use ito siyang iyang formula, no? So supposedly the formula here will be so the voltage from here, so from feeder, so that is 186. So 1.86 plus this voltage drop 3.17 over 230. So muna yung ilang igamit ng formula. So even if that is for the branch circuit already. 1.86 plus 3.17 times 100%. Okay, so the total percentage now is 2.18. So if you look at the values here, so 2.18, so more or less the same lang sa din siya. So 2.18 dire, if you calculate it as a whole, 2.19, but if we add this, can you see and can you see so approximately close to that value already. So 0.81 plus 1.39. Okay, so I have here 2.2. So while here we obtain 2.19. So again, this is the total. So this is the feeder plus branch circuit. Okay, then supposedly, if we are going to do that, so dapat ang ato ang no? Ang atong max value is 5% for this feeder plus branch circuit. But again, to be safe, so dili sila mo rely itong value nga maximum. So they have to adjust the value so that safe may lang calculation. So they just going to use 3%. Okay, so yeah, so more to ang calculation for voltage drop. Then for the next part, so we are going to calculate also the uh, fault calculation for our design. Okay, so I'll just add it here. So for now, so kanila sa inyo ang basis now. And I'm going to give you an assignment later on. So it's a by group na assignment. So in which you are going to design, for example, tagaman ako yung nani, then you calculate the demand and you calculate the voltage drop for this for whatever design that you come up with. Okay, then that will be again by group and I'll give it later. So wala na ako naman ng problem. But for now, so question about the calculation of voltage drop.
And so far, sir.
Okay, so again, so we're just dealing here single phase. So if ever you encounter, so ako na lang sa take note, if you encounter three-phase problems, so in our table, so we are given also with kono since ang given at our to mga line current mo to siya. So automatically you can use it already for your line current. Then for your voltage drop, so ang imo lang basihan is kanilang siyang voltage tire or either of these conductors. So ako ano lang sa no, I'll just give an example later sa I'll just add it here. So formula lang ako ihatag diri sa voltage drop calculation if ever you encounter three-phase nga load. But for kanila siya nga design, single phase naman siya, so we don't have to use it. Okay? Since it's already time, so masimutaas sa akong discussion. So if you like the question, so that's it. And expect again assignment. That's by group. So where you have to design and calculate for the voltage drop. So that's it. And thank you. You may now leave.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.